Yeah, I think we can start the next sessions, and maybe I can skip some slides since we already introduced in the previous sections on what is the GPTG, its details. So here I will introduce the gScale, which is our solution to improve the vGPU instance densities. So currently we support 7 VMs plus Doom 0. And we were trying to support at least like 16 and even more with this gScale solution. And gScale is actually just a name, and the background is using the dynamic resource sharing among the multiple VMs. So yeah, his agenda is here. We will first introduce the vGPU scalabilities, currently and GPTG solutions. And we will introduce the challenges we have and how we doubled our vGPU instance densities, and we'll provide some performance data. Okay, I think we can just skip this slide. Okay, one thing we need to mention here is the GPTG is mediated pass-through, so the performance is relatively good compared with the native side. And currently, as our measurement, at least like a 2D workload or 3D workload, we can get at least like the 80% compared with the native. And particular case, for example, on Housewell with the median transcodings, we can achieve almost like the 99% of the natives. This was good, and it is a full GPU virtualization solutions. So basically, everything you can run in native side, you can run on our guest without any problems. It supports DirectX 12, DirectX 9, and 10, OpenGL, OpenCL, and also like the Intel Media SDKs to support the media transcoding and the encodings. And currently GPTG support 7 VMs plus 1 Doom 0. And applied with our gScale solutions, we are trying to increase the densities to at least 16 and or even more. So to understand this, we need to get into the details of Intel processors. So as I just, so here is a very high level pictures. So GPU access system memories by his global page tables and processing graphic page tables. We call it a GGTT and the PPGTT. And there is several components where we're accessing the system memories. The first thing is the render engine. So this one is the major engine executing the workload, the 3D workload, 2D workload, medians, so everything going into these render engines. And this engine will access both GGTT and the PPGTT. And the next component is the display engine. So this one is very straightforward. It will get the frame buffers, go through with the GGTT and gets the frame buffers here and provide you the screens. And one more component we call it access from the CPU side. So when we CPU, we're trying to read the frame buffers or maybe the intermediate decoding the frames, want to do some processing. He will go in to access the apertures. And then GPU will provide his fancy ID to facilitate CPU access the system memories. He will also go into the GGTT page tables and finally access to the system memories here. So here comes the problems. We have single GGTT page tables, but we have several components from the CPU access, from the display engine access, and from the render engine access. So this is the more clearly on these problems. So we have several components in parallel access the GGTT here, and on native it's okay because there is no virtualization support. But once we get into the GPTG solutions, since the render engines, I will back this one. The render engine is actually shared by the multiple VMs. So this is the time slice time slice shared. So at the one over specific time, the random engine was assigned to one of the guests, and that guest will push the workload. And but at that time, CPU from another VMs will trying to access his graphic frame buffers or maybe the other system memories. So in the end, the GGTT need to provide all of the mappings for different VMs. That means he need to handle requests from the VM1 from CPU access. He need to handle the VM2 from the CPU engine's access, and also the VM3's random engine access. So here comes our gGTT page tables. We need to include every mappings from all of the VM access. So here comes our solution. Just as I mentioned in the previous sections, we need to static partition these gGTT page tables here. So this is like the page table. We have a range of 4 giga. This is an example of 2 VMs. So if there are 2 VMs, we need to static partition into 2. So with this design, so every VM will access his part, and the CPU access from VM2 can continue running for example, like the brown side, and the random engine can access the green side, and there is no configurations. So here comes our design for the current design for ZenGT. So here comes problems with this design. Here is the 2 VMs, but once we increase the VMs numbers, we cannot support it anymore because in a guest, there is a minimum requirements for like the aperture size and also for the invisible graphic memory size. For example, if you are typically for a Win8 to run a 3D workload, he needs at least 128 aperture size, and plus with 384 mega for the invisible graphic memories. So if we want to support seven VMs, so this is the maximum numbers we need to support with these static partition solutions. So currently we can only support 7 VM plus DOM0 because of this minimum requirements for the guest side. So how we to break these resource limitations? So here comes our gScale design for how to double the GPU densities and how to increase the GPU numbers. Okay, since the problem is coming from static partition for the global page tables, so it is very simple that we will remove these static partitions. Instead, we will allow every VM to have his own global page tables. Left side is original design, and the right side is we have 2 global page tables. And we will load and switch global page tables during our VM switches, because most of the gGTT table access was coming from random engine side. Maybe like the 99% were coming from the random engine side. So when we switch the random engine, we switch his page tables here. With this design, the key challenge is there are still 2 components, just I mentioned, the CPU engine and the CPU access. We're still trying to access his from different VMs. So how we to remove this in parallel access? So we will discussing the one by one with 3 components access, random engine, the CPU engine, and also the CPU access. And the CPU access actually there is several types, tied memory and non-tied memories. Okay, with the random engine access, just as I already mentioned, every VM will have his own global page tables, and the global page table access mostly are coming from random engines. Maybe like the 99% of the access was coming from random engines. So we prevent this per VM global page tables. We load this table to hardware when the hardware was assigned to one of these VMs. So by doing this, most of the case is okay. we can run 3D workload, 2D workloads without problems. But once you have a CPU access to the aperture, or you have a display engine want to get the memories from free buffer from VM2, these two components cannot get these informations because these entire tables do not have any mapping to the VM2. So here comes our solution to the render display engines access. So as we described, it was currently the global page table was assigned to VM, the green part, for example, the VM1, and there is access from the VM2 to the display engines, the frame buffers from the display engines. So what we do is, at the beginning of the part, we keep this range unchanged. So there is always, like, for example, 1 to 128 mega. This range was not changed during our during our global page table switches. And the same frame buffers here will have duplicate mappings. One is from the render engine access from this path. And we will also prepare this mapping in this reserved memory, reserved range here. So this range will keep every VM's mappings here. So no matter the global page table was switched in or switched out, you can always go into this path and find his frame buffers. So here is the way already addressed how to handle the display engines in parallel access. Okay, so now go into the tied and non-tied memory access from the CPU side. This is a very simple introduction on what is a linear service and what is a tied service. For linear service, the data was stored in the memory with in an order, and the CPU will access also in an order, so he can read the data like this one, read a service like this one. But for a tied memory, the data was stored in the memory was disordered, and this is because for the optimization for the GPU access. But CPU will read still with the in order read, so CPU point of view, he gets the picture like this one. So the CPU to access the tied memory, he cannot directly use that. He needs to get the help from the GPU side. So here comes with the two difference. If the CPU were trying to access the non-tied memory, it is a linear memory from linear service from system memories. So actually, CPU can directly read these data here. Because we prepare the global page tables for the guest, so we know the machine agents here. So we just prepare the APT tables for that vCPU and for that guest. So when the guest is trying to read the frame buffer or maybe the graphic memories, he just go into this EPT table and bypass the graphic path and then go into directly to the access system memories here. So by this way, CPU access will always bypassed and to the system memory directly. We can do this because the currently Intel design is the GPU access and the CPU access, they are cache coherency, so there is no cache problems. Okay, so going to the 6x access for the tied memories. So this is a different path. We need to get the help from the GPU side. So typically, CPU access to the EPT table to the to aperture size, and GPU hardware, we need to get the fence registered from the GPU hardware, and this fence registers will help to reorder the data for the CPU, and this fence ID will go into the global page tables and find out this page table memories here. So it will go into the global page tables again. It's very similar what we have to handle with the display engines access. So how we handle in display engines, we reserve a particular range in the beginning of the global page tables. So this range will not change during the global page table switch. So in that case, it's the same way, the CPU access will always like the limited into the this reserved range. So when we CPU trying to access particular frames, for example here, we will dynamically create the mappings in this range, and the CPU access will go into this path. Okay, so now both the three components like the CPU access, display inch access, and the run inch access, they all can in parallel access now. So here is a summary. To access the system memories, there is 4 paths and 3 components. The path 1 is CPU to access the non-timed memory, and the other 3 paths is going to the GTT page tables, and we will switch the GTT tables here according to the random engine switch, but we will reserve the kind of memory, memory range for the display engine access and the CPU actual access. So okay, so by this stage, we already well overcome the issues we have. Okay, here comes our optimizations here. Because global page table size is 2 mega, so it is pretty large, and content switch is very fast. Our scheduling is like 1 milliseconds to 10 milliseconds, and we will switch the contents for different guests. So it is very time-consumed the job to switch the global page tables, load and the restores saved. So as our optimization is, we will split the global page tables into several slots, and every slot, because the guest will not use the all range of his global graphic ranges. For example, the VM1 and the VM3. So VM1 and VM3, they share the slot 1 in the low memory size and share the slot 1 in the high memory space. So before this slot, they are different, but all others are same. So when we switch from VM1 to VM3, only thing we need to do is to change this slot to VM3, change this slot to VM3. So this is what we need to do. And we don't need to switch the entire tables here. So here, we reduce lots of CPU cycles here. So here comes our performance collections. We have a collection on both Linux side and Windows side. Oh, actually, these data are coming from the Usenix ATC papers, 2015. So we just published the earlier of this year, and this slides actually the data were coming from these papers. Okay, with these data, with these optimizations, with the red part, our total performance penalty is around like the 5% compared to the scheduling of VM switch. And without these optimizations, it is up to like the 20 or 30%. And on the Windows side, it's similar. And with this optimization, it's much better than without this. Okay, so now comes to our real world, how we run the workload and what looks like the final performance. So again, we measure in the Windows guest and the Linux guest, and we normalize the data on single VMs with 1%. And then we increase numbers from 4 VM, 8 VM, and 12 VMs. And we can see the performance. Even on the 12 guests, the total performance is around above the 80% of a single guest. On the Linux side, a very interesting thing is with the 2D case, the multiple VMs was get even better than the single VMs. This is because in a single VM, the GPU capability was not fully utilized. But with this increase of our VM numbers, we burn out the CPU powers, so it gets more performance data. But overall, it is even with the 15 guests, we can get the performance like above 80% compared to with single VMs. So here comes to our summaries. So gScale, actually this is just a name of this our solutions. So this breaks our graphical memory resource limitations. So we can increase our density to 16 or even more. And the scalability looks good. Even with 12 or 15 VMs numbers, we can still get the performance like the 80%, even more. Okay. So here comes our resource links. It is very, everything actually, you can get the information from here. And our quarterly release notes will also published in this our website. And the following is the other components, the links. Okay, so any questions?
So just to clarify my understanding, your bar space inside each of the VMs is pointing essentially at a private global GTT for that VM. And then when you schedule a particular vGPU instance on the GPU, you swap that global GTT into the actual global GTT of the hardware at that point.
Yeah.
So the guest CPUs have got free, unhindered access to their own private GTTs on an ongoing basis, so you don't have to schedule the VM vCPUs and the GPUs in any sort of gang mechanism. They can still be scheduled independently, yeah. You haven't had to do anything to the Zen scheduler is what I'm getting at.
You mean the schedule? Yeah, actually, we switch the global page tables when we switch the random engines, and the per processor GTTs. This is not the problem. This is because this was only accessed by the random engines. There's no problems. The only case is the global page tables, and we switch only for that global page tables.
Right,
So
but you don't have to block CPU access or anything because each one has its own private.
Yeah.
Yeah. Okay. Cool. Thanks.
Okay.
What were the workloads in your benchmarking numbers? So you were showing the performance degradation with.
Let me check. It should be like the Heaven or 3D Max, but the details were in these papers.
Okay.
Just abstracts the performance data here. Yeah, the data was crashing on the E3 machine.
So this 3D Mark number on the left, right? This is with gScale active, right? So the single VM number that's normalized to 100%.
Yes. Yes.
Then when you show 4, 8, and 12, those are all with gScale active, right?
Yeah.
So you could do 4 VMs, right, without gScale, right?
Yes, we already can do. Currently, we support 7s. So this is for gScale.
Okay.
Without gScale, actually with the static partitions.
So to get a real picture of how well gScale is performing, you really need to show what that 4 VM number looks like with gScale and without it, right?
Okay. Yeah, maybe this was in the papers, but here just collect the some of the data. Okay, I think the pretty much. So thank you, everyone.